Binary is the natural language for computers, but it's not so natural for humans. To resolve this communication impasse, we need some way to convert human entered decimal into binary, perform those calculations in binary, and return the results back to the user in decimal again. Everyone gets to work in their native language, and everyone's happy. An n-bit binary code is a group of n bits that can assume up to 2 to the n different combinations of zeros and ones. Each combination represents one element of the set being coded. It's obviously good to have unique code since we like to avoid ambiguity in computer science. When we're encoding decimal values, we need to have 4 bits to accommodate the 10 digits from 0 to 9. Several different encodings are obviously possible, but the one that you see in this table is known as binary coded decimal, or BCD. Because we have the extra bit for 0 through 7, BCD uses more bits than just storing the number in binary. BCD is important for input and output. For alphanumeric values, we often use ASCII, or the American Standard Code for Information Interchange, which was first introduced all the way back in 1962. ASCII uses 7 bits to encode 128 characters. In the arrangement of this table, the 3 most significant bits determine the column, while the last 4 determine the row. You may even notice that column 011 has all of our binary coded decimal numbers. In looking at ASCII, you'll notice there are also 34 control characters. These control characters can be divided into 3 types. Format effectors, for example the horizontal tab or HT. Information separators, for example the record separator RS. And communication control, for example start of text or STX. You may recall from somewhere in your study of computer science that computers work quite a bit with 8-bit quantities known as bytes. So, with ASCII, we store the 7 bits for the ASCII and add a 0 at the beginning. We could add another 128 8-bit characters with the most significant bit set to 1 for specific applications such as printing. We can also use that 8th bit as a parity bit to detect for errors. Dating from the 1980s, Unicode is another standard for encoding text expressions. It uses 1 to 4 bytes in the UTF-8 character encoding for 1,112,064 characters and covers most of the world's writing systems. There are also UTF-16 and UTF-32 character encodings to represent even more characters. Parity bits can be used to detect errors in communication and processing. A parity bit is an extra bit that gets included to make the total number of ones in a word either even or odd. We put this bit in the first position. We can use the 8th bit of an ASCII code as a parity bit to check if things are correctly transmitted. In our communication protocol, we'll decide on either even or odd parity. When a byte gets transmitted, we then need to check if there's a single bit error. If there's an error, we send back a negative acknowledgement, or an NAK. If everything is cool, we send back ACK for acknowledge. When we use the standard binary code to count, the number of bits that change from one number to the next varies quite a bit, as you can see on the left-hand side of this table. We can have anywhere from between 1 to 3 bit changes from one number to the next. For example, going from 011 to 100 means that all 3 bits have to change. Most of the time this isn't a problem, but some applications can have trouble with multiple bit changes. Gray codes were invented by Frank Gray at Bell Labs in 1947 and only have a single bit change at each time period. There are several different types of gray codes, and you can see the binary reflected gray code in the right-hand side of this table. Page 32 of the 5th edition of our text has an algorithm for constructing the gray code if you wish to do so on your own. Pictured here is an optical shaft angle encoder, which is a disc attached to a rotating shaft for measurement of the rotational position of the shaft. Clear areas correspond to binary 1 and opaque areas stand for 0. On one side of the disc we have an illumination source, and on the other we have a sensor for each of the bits. Using traditional binary codes, we can run into problems such as the boundary between 011 and 100, whereas the gray codes on the right change only a single value. Gray codes also have reduced power consumption demands, so they find use in complementary metal oxide semiconductor or CMOS circuits. We'll also see them in combinational logic circuit design when we look at Karnow maps, and in the design for the sequence recognizer in the sequential circuits chapter. This concludes Module 1. Make sure to check off your boxes on the lessons page for this module, and to complete the homework assignments associated with the module. Thanks again for watching.